Okay. I'm going to continue roughly from where I left off, and I'm going to go over some of those things again. I was listing some properties or results, and I'm going to talk a bit more about actual proofs. So, and the underlying questions is really the connections between type 2 matrices and quantum automorphisms, which is interesting. Really, I don't understand it at all. So anyway, the situation is we're given a type 2 matrix W, ordered by N, and we're going to find matrices Y sub ij, okay, in this form. Now, just to remind you, this is the ratio of two columns of I, and this is the the ratio of two columns of I transpose. So this is a something like an outer product. Now, it's immediate from the definition that the Y sub I is equal to the 1N times I. So we've got two identity matrices, and we could also see that the transpose of Yij is Yji. If W is flat, then Yij is emission. And it's almost worth calling out an exercise. And I sort of firstly down here, and you might also, it's also so easy to see that this is true. You know, the thing going on here is that all you can really use is the fact that W times W inverse transpose equal to N times I. Now, the point is when you can multiply W, a matrix times its transpose, you're effectively taking in the dot product of two rows. Okay, so what you're doing is taking the dot product of a row of W with a row of W inverse. Okay, so you put, in other words, you pick a row, you pick a second row, you replace each entry by its reciprocal, and then take the dot product. And this is telling you that result of that process will be N if you're using the same row twice, and otherwise it will be 0. And so you have that relation. And so that's going to drive everything that we do. So the point then is that these guys are idempotents. Okay. And so, I'll go on a second. So we're going to define script Y, so W to be the N by N block matrix with I entry Yij. And we call it the matrix of idempotents of W. Now, this should remind you a bit of a quantum permutation. Okay, in a quantum permutation, you put in the entries of projections, and these are in general not projections. There are interesting cases where they are, so, and we'll be discussing that, but they're not required to be projections. Okay. This matrix is symmetric, and there's a few properties there which I'm not really going to need much, so I'll just leave them in there for you to look at. But so we have this matrix, the entries of projections, we're not requiring them to be orthogonal projections, they need to be emission. Okay. Now, sometimes they might be, but that's another story, which we'll get to. So the little fact from matrix, there's in some sense 3 ways of defining the product of two matrices. One is to say, well, the Ij entries are sum of Aik times Bkj, summed over K. Okay. The other definition is to say, well, you take a row of A and take its dot product, so to speak, with a column of B. And the third way, so that's using the inner product. The third way is to use the outer product. And so we have this identity here. And so this is just multiplication written in a different form. Okay, but it's quite useful. So the point here, AI is a column, major convention, this is a row, and so this is a sum of rank 1 matrices. Now, this is not a formula you'd want to use because you'd have to create these rank 1 matrices and then add them all up. So the other ways of doing it would be more efficient, but it's still useful. Okay. In this particular case, well, it's useful here where you know that W times the W zero inverse transpose is N times I. Okay, so I'm just going to apply this identity to that, and you get that the this is equal to n times I. So I'm just writing this using the outer product formula. Okay. Now we just go back. This is essentially this is the entry of our matrix script Y. So these are idempotents, and they're, well, not quite, but they're just our idempotents, and they're summing to n times the identity. Okay, so we get that. Now I want to look at this in an equivalent way using something which I originally called a dual basis. So the assumption is on given vectors x1 through xm in a vector space, but, well, an enterprise space probably with, and then the second set of vectors y1 through ym. Now we say the second set of vectors form a dual basis if the products yi transpose xj equal delta ij. Now you can take V to be an enterprise space, but basically our enterprise space is going to be real, so I'm not going to fuss about that. So the nice thing about a dual basis is if there is a dual basis, that certifies that x1 through xm are little independent. Okay, in fact, that's if and only if. Let me scribble this down in blue. So if I write down the matrix, if I write down the matrix y1, yn transpose x1, should be an m. Then this should be the, so if the y satisfy this, then these columns form a dual basis to this. So if you want to say a high-flown way, you can say that these vectors have a dual basis if only if this matrix x1 through xm has a left inverse. But let's not worry too much about that. So there's just ways of looking at it. But the point about dual basis is that there are times when it's actually easy to see that there's a dual basis, and that lets you satisfy very quickly that a set of vectors is still independent. I'm not requiring that x1 through xm be an actual basis. Okay, I mean sometimes it will be, but I use the term dual basis in a slightly more general sense. Now the point is, if given a dual basis, well, this is the equation. This equation here tells is this. Now this is saying that y transposes. Now it's probably easy. We're going to assume at this point that n is equal to dv. At least I wasn't explicit. And so this tells us that y transpose is inverse of x, so I can swap the x and y, and then I use my outer product trick and I get this sum. Okay. Now it's very easy to check in this case that the product of two of these guys, you get a y transpose times an xj, that's delta ij. So the rank 1 matrices xix transpose is a set of pairwise orthogonal idempotents summing to the identity. So we're trying very hard to be a quantum permutation. The only problem is that the entries are not required to be projections, they're only required to be idempotents, but they sum to the identity, they're pairwise orthogonal. Okay. Now, stop to think about this. Well, one thing really, first thing is that this generality is actually, it works. It covers some useful things. There's stuff we can do with it. Okay, and so it's not much harder to, well, it's not really any harder to work at this level of generality and then specialize for the flat case when we need it. And that is already a bit of a surprise because, you know, usually if you get something that works nicely like a quantum permutation and you start making small changes in definition, it all blows up in your face, but it's not. So continuing on this, on the algebra theme, now if a matrix M commutes with xi y transpose, then of course we get this. Now this is rank 1, this is rank 1. The column space of this is spanned by xi. The column space of this is spanned by mxi. These two things are equal. So the span of xi is equal to the span of mxi, and that tells you that xi is an eigenvector. And just for a change, I'm using lambda as the eigenvalue. Okay, and a similar argument tells you that y transpose m is a left eigenvector with an eigenvalue, which I'm going to temporarily denote by mu. Now, if we compute the trace of these two guys, now these two traces are equal. This trace, so the mxi just gives you a lambda, so you get trace of lambda on this, so you get lambda, and trace of this is mu, so you get the lambda is equal to mu. And so this tells you that if m commutes with xi yi transpose, then xy is a right eigenvector, yi transpose is a left eigenvector, and they have the same eigenvalue. Okay. And so that's what I've written down here. Okay. So we have that. Now, assume now that if that probably should be a lambda I. So assume that we've got eigenvectors x1 through xn for m. If m and xi, xj, yj transpose commute for all j, you can't tell us j or I, so one fast. And you've got m is equal to m times the identity is equal to m times the sum of the idempotents is equal to lambda I, xi, yi transpose. And so this is looking a lot like a spectral decomposition. The main difference is that these are not emission. Well, neither is this, so we can't expect it. So this gives an analog. Now, this will only be correct if the this sum n is the dimension of the underlying space. So what we've done here is construct a spectral decomposition for diagonalizable matrices because I require a basis of eigenvectors, and a matrix is a basis of eigenvectors for a matrix if only if the matrix is diagonalizable. Okay, so we've extended the definition of spectral decomposition from symmetric matrices to diagonalizable matrices. Now, it turns out when you, for purposes of numerical work, when you're trying to do real calculations, the nice matrices to work with are the matrices that are normal. In particular, if a matrix is normal, then its behavior is to a considerable extent controlled by its eigenvalues. If the matrix is not normal, that is no longer true. And a diagonalizable matrix doesn't have to be normal. So there's some numerical reasons why we work with this spectral decomposition the way we normally do with those assumptions we have. But the point still is that if there is a basis of eigenvectors, then we can get something that looks very much like the spectral decomposition. Well, it is like the spectral decomposition. And so we're just going with that. And so the consequence of this is why is the matrix of idempotence of an n by n type 2 matrix, each row and column of y sums to the identity, and if W is flat, then the matrix of idempotence is flat, and hence it's a quantum permutation. So the summary is that a type 2 matrix gives us a matrix of idempotence, and if a type 2 matrix is flat emission, and if type 2 matrix it's a flat unitary matrix, then we get a quantum permutation. Now, and so from this point of view, we've got a slight generalization of quantum permutations. Now, we're not really concerned, in this course, we're not concerned with the generalization. If you're interested in spin models of link invariants, then the generalization is very important. But for the purpose of the quantum stuff, we're really only interested in what happens in the flat case. Now, it's possible that could change one day, but as things stand, for the quantum situation, the type 2 matrices you're going to deal with will be flat type 2 matrices. And they do come up in a number of places. There's work on so-called symmetric informationally complete POVMs and mutually unbiased spaces where you get flat type 2 matrices appearing, but we're not going into that. So, but still, as I said, the summary is that if I have given, well, probably the important thing is if you give me a flat unitary, I construct a quantum permutation from it. Now it's got a special form, and we'll see more about that as we go. But each flat unitary determines a quantum permutation. And in a sense, we're in an unusual problem where instead of saying, here's a graph, what are some quantum automorphisms, we're in a situation where we've got a quantum permutation, and we ask, what is an automorphism of? So I'm going to continue working with this. I'm just defining the swap operation on Cn tensor Cn. So it just maps the vector A tensor B to the vector B tensor A. Now, S is a permutation because it's just permuting the elements of a basis. These guys, the vectors of this form span, and they contain a basis. And so S is defined on a basis, and it's a permutation, so S squared is the identity. And the claim is that if W is type 2, then S times Y sub W times S is Y sub W transpose. And the point is that type 2 matrices always come in pairs, W and W transpose. And the connection is interesting and useful. Well, basically, you just go through and replace things by their definitions. And there's no point in me going through this in any detail now. I've got nothing to add. You go through these definitions, you get that these two guys are equal. And then you think long and hard about what. So EI times ER matrix, EJ times ES, you're picking out the IJ entry. The trouble is that the tensor, instead of having, because this is we're dealing with the square, the product of two tensor product of two matrices. Instead of having indices I and J, we're going to have indices II prime and JJ prime. And so that's what's happening here. But so, in other words, this is just another way of saying this. We're taking the RS entry of YIJ, and that's, we can write that in tensor notation like this. So we get this result. So there's nothing deep in this. You just have to grind through and try and keep your tensor products straight, which I can otherwise do. Okay, so and so this will be useful. This means we can prove things about Y sub W, and we'll get things about Y sub W transpose more or less for free. Now, to present some of the results, I'm going to use bracket notation. This is not the Dirac, silly Dirac bracket notation of the physicist love. This is the Lie bracket. And so it's a Lie product. Think of it as a product of two matrices. It can be a bit more general. And so, but I've got two matrices the same order. Then the bracket of M comma N is defined to be this. I think I'll put it in now. So this is bilinear, so it's linear in M and linear in N. And it's skew-symmetric if you swap M and N, the sign changes. It's not associative, but as I said, it's linear in each coordinate. Now, I'm just using this as a convenient notation because I can say that matrices M and N commute if and only if yeah. So M and N equals. Actually, it's not altogether clear why, but I sometimes find this slightly more convenient. Okay, but we won't be doing any, so I'm just using notation. We won't be thinking about the algebras at all. Now okay, so we have the following theorem. If Y is the matrix wide idempotent for type 2 matrix W, then the Nomura algebra of W, so these are the matrices that have the column ratios of W as eigenvectors, consist of the matrices M such that I tensor M commutes with Y. And the Nomura algebra W transpose is just N tensor I. The matrices N such that N tensor I commutes with Y. Okay, so now, and so within now, we'll see in a little while the matrix, so it follows from this that the matrices N and NW transpose form a coherent algebra. This is a quantum. Well, it's a good point. It's going to follow what we do. Certainly, if y is flat, we get a coherent algebra. And in that case, we would have a quantum permutation. So you're getting quantum automorphisms of the graphs in the coherent algebra. And so we have some sort of a connection between the Nomura algebra and the quantum automorphisms. The only place where this connection is written down is basically in these notes. And it's not entirely clear what we can do with it, but it's something of interest, considerable interest to us. Okay, so we claim these two relations. And basically we just need to prove one, and then we use our y sub w S trick to convert to the W transpose. Notice these are both the matrix of idempotency of W. There's a bit of this could have been the matrix of idempotent W transpose, but it's not. Okay, it doesn't matter too much because we've established now that the relation between y sub W and y sub W transpose, well, one's just a permutation of the other. Okay, one is permutation equivalent to the other. And so, okay, so the proof. So I'm proving the first part. Now, let's think about, I'll go back to my view again. I tensor M is block diagonal. It's copies of M down the diagonal. And Y is a block matrix. So if these two guys say you've got M down here and you've got blocks Y, I, J over here. Now, if these two guys commute, you see that M must commute with each of the blocks of Y. Okay, and that's why I was doing that stuff about, okay, but these are rank 1 matrices. So if M commutes with Yij, then the column space of Yij is an eigenvector space, or the columns of Yij give you eigenvectors for M, and the rows give you left eigenvectors for M. So we, so this is what I'm just saying here. If M commutes with all these guys, there's no S is a rank 1 right eigenvector. So that gives us that M is in it. So if M, that tells me that M commutes all these things, and therefore it's in the Nomura algebra. I probably shouldn't have written a star there, but you get the idea. It doesn't affect anything I'm doing. For the second claim, we just use the fact that we're applying S to this, where we put an S squared there. And so S and tensor IS is I tensor N. That's what S does. And S like S is Y sub W transpose. And so the conclusion then is that if W is type 2, then NW is a commutative coherent algebra. If Y is equal to the matrix idempotent W transpose, then Y is a quantum automorphism of each graph in NW. And I probably should say, let me be a bit more precise here. So if W is not flat, we're getting something, a generalization of a quantum permutation. Now, there's resulting in the state, the proof is in the notes and in various places, a paper by Ada and me, but it goes back to the Nomura. And this is giving us information which I haven't proved yet, and I would like to be able to derive it from playing with matrix of idempotence, but I haven't succeeded in doing that yet. If W is an M by N type 2 matrix, and M is in the Nomura algebra of W, then the matrix of eigenvalues of M is in the Nomura algebra of W transpose. So the map theta is taking elements of the Nomura algebra W to the numerical algebra W transpose. Okay, and the image of a matrix product M times N would be a Scher product. So we're dealing with an algebra of here's closure multiplication that follows it. Then this guy has to close on a Scher multiplication. And we also find that if M and N are in the numerical algebra, then the image, the matrix of eigenvalues of the Scher product M times N is equal to the product of the images M times N with the factor of 1 of N, so I need to confuse things. So that tells us, and so it's this that tells us that the numerical algebra is Scher closed, or both sides are Scher closed, because this is essentially implying that if you take, well, theta W maps the numerical algebra, I could write this down. So theta W, sends NW to NW transpose, and theta W transpose sends NW transpose to NW. And so the composition of these two guys maps NW to itself and NW transpose to itself, and you can check that so basically the composition is basically the transpose map. So it's invertible. So that gives you. So this is an important result. It's due to the mirror. It could be proved with the same amount of difficulty as anything else I've been doing in this last lecture. In this lecture, last part of the last lecture, is not spectacularly difficult by any means. I don't have a nice proof using the matrix of idempotence. I'd like to have one. Good on that. Okay, so we have this relation between, so type 2 matrices give us matrices of idempotence, flat type 2 matrices give us quantum projections, and we have these numerical algebras, and so and they're related to the automorphism groups of quantum automorphism groups. Well, that's all very well and good, but it'd be nice to have some examples. And this is a bigger problem than might appear at first, but we'll soldier on. So the simplest case to deal with perhaps is to take the van der Waals matrix again. Now it's type 2, and the important property of the van der Waals matrix is that the Scher product of any two columns is a column of the van der Waals matrix. Okay, and the Scher ratio of any two columns is a column of the van der Waals matrix. So in fact, the columns of the van der Waals matrix form a group under Scher multiplication with the Scher inverse as the inverse map, and the all one vectorized identity. So you have a Scher group, which we won't go into now. So there's that nice property. Now, if P is the permutation matrix of the N cycle, then P is in the numerical algebra of V, because each column of V is an eigenvector for P. Okay, and so therefore that implies it's in the numerical algebra by definition. And in fact, this is just linear algebra. You don't have to. The V is the algebra of the N sub V. Is the algebra of polynomials in P. And I may even assign this an exercise. The point is that the eigenvalues of P are distinct, and so its image in and so theta of P will be a diagonal matrix of distinct diagonal entries, and so you can use that to show that NW is in fact the algebra of polynomials in P, i.e. the algebra of circular matrices. Okay, so we know what the numerical algebra is in this case. I'll do a little exercise there. And I said that's in some sense purely linear algebra. You don't have to know about type 2 matrices or quantum permutation or anything. You just do a few calculations along these lines. So we get the algebra of circulars. Okay, so we know the numerical algebra. That's okay. And so that's nice because then we have that relation between the numerical algebras and the things that commute with I tensor M and so on. So we're in reasonable shape. But in this case, we discover that the bad news is that all entries of Y commute. Now, that's not entirely trivial. The entries of Y in this case can each be written in the form X, XY starred, well, more precisely, XI times xj starred, where x1 to xn run over a collection of eigenvectors. And so from that, you can show that the entries of y commute. And so we don't get any, interesting quantum automorphisms. Now, I'm mildly annoyed that we have this concept of a quantum automorphism group, which I'll say a bit more about towards the end of the lecture. Okay. And so you would expect that the elements of the quantum automorphism group would be called quantum automorphisms. But the people in the area seem to be reserving quantum automorphisms for the elements of the quantum automorphism group that are not classical. Okay, so the terminology is a little bit confusing. But the point is that we can, we take the van der Waals matrix, we can determine the numerical algebra. We know the entries of W. We get a quantum permutation. That's the good news. The bad news is that it's a direct sum of permutations. Okay, still it works, now the second class examples, I want to work with Hadamard matrices. Now, so I'll start with an n by n Hadamard matrix. Now, a general comment here is if W1 and W2 are type 2 matrices, then the numerical algebra of W1 tend to W2, which is a type, obviously a type 2 matrix, is the tensor product of these two neural algebras. And again, this is reasonably straightforward. We'll probably turn up on the exercises. Now, the dimension of any numerical algebra is at least 2 because it contains I and j. If it's only 2, it's something that's trivial, and I've been saying that word around before very long. So, for example, we can get a numerical, but even so, we can get a numerical algebra of any dimension we want, or any large, of any larger than the integer you give me. So there's a range of values. It'll turn out this is not a very interesting construction, but it's just keeping in mind. So this is actually saying what I said before, that if I have a flat type 2 matrix and the set of columns W is closed under shared multiplication, then all entries in YW commute. And there's the actual proof. It follows that if W is a Kronecker product of if W is a Kronecker product of van der Waals matrices, then the entries of YW commute. Now, one reason this is important is that I said that the van der Waals matrix is a type 2 matrix, flat type 2 matrix. More generally, the character table of any finite abelian group is a type 2 matrix, but the character table of any finite abelian group is a Kronecker product of van der Waals matrices. So this is telling us that even if we go past beyond van der Waals matrices and cyclic groups to more general abelian groups, we're not going to get anything, any quantum automorphism with non-commutative entries. Okay, so we can't do any better at tricking away. I've got the Hadamard matrix here in the middle. So when I say numerical algebra is trivial if this dimension is 2, as a result, due to Jaeger and probably others, it says that if H is an n by n Hadamard matrix and the dimension is greater than 2, then H is divisible by n. I mentioned this just to show you there are restrictions. So we know if you have a Hadamard matrix of order greater than 2, it's automatically divisible by 4. If you want the numerical algebra to have dimension greater than 2, then there's a restriction on n. Now, the bad news is that for all known Hadamard matrices, the entries of the matrix of idempotence commute. Now, all known means Hadamard matrices up to order 28. URA did the calculations many years ago. I don't know if there's any written record anywhere. So the smallest open case is on 32. At the time we were doing that, there wasn't a table of the, we didn't have a list of the Hadamard matrices of order 32. I think there is one around now, so it could be pushed to 32 if anybody really cared. It's not at all, well, I have no real idea. I mean, you can go on with the Hadamard matrix where the matrix of idempotence has got non-commutative entries. If it is, the smallest example is on 32 vertices, or 32 by 32. In a sense, okay, we've got some. So using flat type 2 matrices, we can get matrix of idempotence and non-trivial numerical algebras, but all our quantum permutations are commutative. And so that's bad news. Now we can get non-committee things if we drop the flat restriction. So there's a limited supply of type 2 matrices that are not flat and have non-trivial Navier algebra, okay, and are not products. You got to be a little bit careful when I say not products. I feel slightly nervous because sometimes when you have a product construction, there's a way of twisting the product a bit. You get something which is technically not a product, but works the same way. So I'm using product in that vague sense. But the interesting thing is that the one family we do have where we get some interesting type 2 matrices is based on the Hadamard graphs, which we discussed before. Okay, so when I discussed the Hadamard matrices, I talked about the adjacency matrix. And so if an n by n Hadamard matrix, the adjacency matrix of the graph can be written as a 4n by 4n matrix in this form, where this H hat is kind of it's the doubling of the Hadamard matrix. So we replace the -1, get rid of the -1. So I get that form. And so in fact, you get 4 matrices to play with. You get the identity, you get J minus I blocks on the identity. So this is just 2 copies of the adjacency matrix, the complete graph on Kn. You get our matrix of the Hadamard graph. And if you think about it for a while, you'll see that this will also, this is also a 0-1 matrix. So we get these 4 matrices and they add up to the all ones matrix. Okay, now, and they're also shear orthogonal. Okay, and so it seems very plausible that these guys could be the basis of a coherent algebra, and they are. Now, if I've been talking about just regular graphs and things, I could do it all using that, but I'm just going to ask you to trust me. So these are the canonical basis of a commutative coherent algebra. Okay, you can check that they commute without any great difficulty. And Nomura proved that this algebra contains a type 2 matrix W, such that W is contained in its own Nomura algebra. And that then implies the dimension of Nomura algebra is at least 3. And this gave a new, means you have a link invariant. As link invariants go, it's not particularly interesting, but there is a link invariant there. Okay, and so we have this situation. So Hadamard graphs work, and so that gives you infinite families of examples. And I think there's a couple. Is there a generalization of these?
There's a twisted product.
No. Yeah, so there are some generalizations of this, but anyway, I'm just giving examples. This does work, okay? And there are some later examples. There's one more example I want to talk about. This is called the Higman-Sims graph. Now, the Higman-Sims graph is a strongly related graph. It was first found by Mesmer. Okay, for historical reasons. Well, one reason it's interesting is it's got an interesting automorphism group, and so there's a group called the Higman-Sims group, and so this is called the Higman-Sims graph, but it was discovered by Mesmer independently and quite a bit earlier. So it's a strongly regular graph. It's a graph on 100 vertices. Valency is 22 regular graph, 100 vertices. There are no triangles, and any 2 vertices at distance 2 have exactly 6 common neighbors. And Jagier showed that if A is the adjacency matrix graph, then there are scalars alpha, beta, gamma, such that this linear combination is type 2, and W is in the same Nomura algebra. Now, this gave an interesting link invariant. Raised a lot of interest. I should say that these numbers, alpha, beta, and gamma, are not particularly pleasant. The same applies to the formulas for the when you're dealing with when Nomura was dealing with these guys. You can find a linear combination of these, which is a type 2 matrix. You don't really want to try and calculate what alpha, beta, gamma, and delta are. It's painful enough to get out of Nomura's paper is quite short, but and it's an interesting result. So we have the Hadamard graphs, and we have the Higman-Sims graph. Now, if you're going to generalize this construction, you want a triangle-free strong. Jagier proved you need a triangle-free strongly related graph with some other properties. And the problem is that the largest non-bipartite triangle-free strongly related graph we know is the Higman-Sims graph. So we do not know a strongly related graph which is triangle-free, not bipartite, and with more than 100 vertices. Now, this has been an open question for at least 50 years, and people are fussed about it. So we don't know if there are more triangle-free strongly related graphs or not. That's an interesting question, and a reasonably important question in its own right, but we don't know. if there are more, there's some chance that we would get more link invariance. This actually gives an interesting link invariant. And so the Higginson graph is interesting because it's triangle free, and so what Morrison group contains the Higginson group, which is a sporadic symbol group, and it contains the Higginson group as a subgroup of index 2. So the Waterloo group of the Higginson graph is not simple, but it's got a subgroup of index 2, which is simple, and which is the Higginson group, and it's one of the sporadic symbol groups, so it's not constructed using Lie theory. And this is just saying what I said about triangle free graphs aren't very common. We have many examples. Type 2 matrices are not rare. Okay. The problem is that the ones we construct almost invariably have a mirage of dimension 2. Okay. So they're related to symmetric designs, to equiangular lines, metronized basis, all sorts of things give rise to type 2 matrices. Just in most cases, except for the cases I've told you about, then the mirage has got dimension 2 or using of products. I'm going for time. Okay. Now, I wanted to I've indicated once or twice that I'm giving you sort of a simplified definition of quantum automorphism. And I thought I would show you a little bit of what we're leaving out. So I'm thinking of my quantum permutations and matrices of projections, and the projections coming from a finite dimensional matrix algebra. Fine. The general definition, you're allowed to play with bigger algebras. You're allowed to use C-star algebras. And so I want to say a little bit about that. So so with C-star algebras, the canonical example is the set of bounded linear maps on a Hilbert space. So, for example, a space of all n-brane matrices acting on C to the n. Okay, so that's the canonical example of C-star algebra. The key parts of the C-star algebra are an underlying algebra, a Banach algebra. I'll explain that in a second, and an involution. And for involution, think conjugate transpose. So the difference between a general algebra and a C-star algebra is the star. You've got this involution acting. I'll explain that now. So an involution on an algebra, whatever the complex numbers, is a map such that the star is the original. Its order, it reverses multiplication, and it's linear over R, but not over C. Okay, so that's what it is. Now, okay, so that's a star. It's a city. I mean, this is, think conjugate transpose, all this works. Okay, so a Banach algebra is a normed algebra. So you've got an algebra of operators, and there's a norm defined. And the important property is that the norm of the product is less than equal to the product of the factors. So most norms you've seen are like that. Okay, so that's a Banach algebra. And so a C-star algebra is a Banach algebra with an involution which satisfies this condition. And so the condition, what this tells you, if you do enough work, is that the involution and the norm are closely connected. Okay, so there's a strong connection between the norm and the involution. Now, the jargon is a compact quantum group is a C-star algebra with a unit. Now, the operator theorists don't normally require the algebras to have an identity, but in this case you do. And you've got a homomorphism, and you won't like this, that maps the C-star algebra to its tensor square and satisfies these two unlikely conditions, which you may be better off not trying to decode right now. Now, I should warn you that when tensor products, there's nothing simple about tensor products. The problem when you're dealing with algebras or normed algebras is what is the norm you're going to use on the tensor product. It's not given to you for free, and so there's some conditions in there. So just defining the norm on these guys requires attention to detail, I would say. And then we have to have these two maps. Now, this map here is called a coproduct. I should write it down. Now, so coproducts are, in a sense, dual with the products, but I don't think you want to know about that right now. But my point simply is that there is a definition of these guys called compact quantum groups. Now, in C-star algebras, you can define projections. Okay, it's an element, an idempotent element, which is equal to its star. Okay, and a quantum permutation officially is an n-way matrix of projections from a C-star algebra with unit such that their own column sum to the identity. Now, even now, I'm still suppressing some complications, some of which are due to the physicists. Okay, but the basic point is that when people like Dave Robertson talk about quantum automorphisms, they allow the projections to come from something bigger than just a matrix algebra. Okay, and it turns out that by increasing the size, you actually get it makes a difference. The concepts are different. Now, for our purposes, it doesn't much matter, since it turns out that it doesn't matter which variant you use. Computing the deciding of two graphs of quantum isomorphic is undecidable, so one's not easier than the other. Okay, and everybody will agree that the quantum permutations we use sit inside the quantum automorphism group. And so my view is that the combinatorial questions we can state nicely just using the definition that we've been using. If you want to go on to the quantum information theory and the relation between the quantum automorphism groups and quantum information, then you will need to go into more details about the definitions. But yeah, if you choose to play with the combinatorics like I do, then you can just smile when they start worrying about whether this is a tensor commuting or a quantum commuting variant. Okay, and so that's it for today.